Any questions? Substitution reaction. Name that molecule. Sounds like a fun game. Anybody wants to create such like this? We can have others. Okay. Anybody interested in creating one? Anybody want this one? Not all at once. Not all at once. Some interesting information. I'm always interested in doing things like that. Kind of learn some things that make it interesting. The relevancy of organic chemistry, right? Organic chemistry is everywhere. Okay, substitution reactions. I'm not sure if I mentioned it, but very important. Very versatile. I sort of downplayed alkene chemistry a little bit, but then I said, well, converting alkenes to epoxides, that's a huge reaction. But epoxides are very versatile. We'll study epoxides organic too. Converting alkene to a cyclopropane, that's very important. So I had to take back there. Alkenes are not as boring or as unuseful as I had said. Lots of important fundamental chemistry there. The main thing with alkenes is forming carbocations, rearranging. Those carbocations are seen many other places, okay, including in substitution reactions, right? Which mechanism includes a carbocation? SN1 or SN2? SN1. SN1, okay? And once you form a carbocation, it can do the same things it did when we formed them a month ago. They get rearranged. Same stability factors, okay? There's many ways to form carbocations. From alkenes is one, from a leaving group just leaving. Okay, let's get it in gear here, Stevens. Here we go. Anybody take a trip to the dentist? Anybody pre-dental, want to go to dental school? Okay, you need to check out anesthetics. You can look up on Wikipedia. Some of these, and you can probably find a page that just covers all these like local anesthetics. Lidocaine, basically your anesthetics, they differ mainly in the duration of action. Some will last maybe 10 minutes. Maybe you want to do a quick procedure, okay? And then you don't want your patient talking around like this all day, okay? It will wear off quickly. But maybe you want to do a longer procedure and you need something that lasts 2 or 3 hours, or 4 or 5 hours. Well, you don't want to be given a shot every 10 minutes. In that case, you want something that lasts longer with a single injection. Okay? Well, that's one of the main differences in the types that are available. And they're all very similar. They have a carbonyl group. And the body degrades them by hydrolyzing the carbonyl. You'll learn that type of chemistry in organic too. Okay? But there's different rates of hydrolysis around the carbonyl. And the ones that last longer have more steric congestion around the carbonyl. It's harder to hydrolyze them, and thus they last longer in the body. The metabolism is slower. Okay? Did we talk about sterics with substitution reactions? Backside, I drew it here. Yeah? The nucleophile has to get in there, and it's like, I can't get in here. I can't get steric crowding, congestion. Okay? Keep it away from me. Thank you. Okay, so that's an important point. We'll see it later. If you want to go to dental school, you need to start looking at stuff like that. Relevancy of organic chemistry to explain drug action, drug properties. Okay. Leaving group ability and substitution reactions. We've already mentioned this trend here. Iodine's your best leaving group of the halogens. These are good leaving groups because when they leave, they become minus. And these atom types are like to become minus. Okay. Okay. Bond strength is also important. A carbon-iodine bind is weaker, so it's easier to break. Let me ask you a question. In which mechanism is the bond to the leaving group broken in the rate determining step? SN1, SN2, or both?
Both.
Think about that.
Okay, cool.
You need to know your rate determining step and what's going on in the rate determining step. Okay? Okay? Understand your rate determining step and all that's going on there. And then ask, well, what is not going on there? Okay? What's going on in the slow rate determining step? What happens then in the subsequent steps, which we call fast? Okay, leaving group ability. Here's an example. If you have this output iodide, you can react it with this. Of course, this is minus, right? That's plus. That's spectator ion. This oxygen anion is a nucleophile, and it can come in here and do a substitution reaction. By the way, is this going to be SN1 or SN2 most likely? It is substitution. Under my hands, iodine. Now it's nucleophile. Iodine, nucleophile. Yeah? You know two substitution mechanisms, SN1 and SN2. Which one do you suggest for this reaction? Why SN2? But you don't want to make it, what type of carbocation? Yes, I mean, if this just left, if it just ionized, you make a primary carbocation, we'd say that's bad. So by default, this is more to SN2. Okay? Sterics, what type of carbon are we attacking here in the SN2 reaction? Primary output iodide. Is there any sterics there? Much? No. Secondary, there'd be more sterics. Tertiary, there'd be so much sterics that what? Wouldn't work. You don't do it right. Were there some exclamation points on that point?
Yeah.
Capitalized and said never. Okay. Never, ever do it. All right. So this is good old SN2 reaction here with a pretty good nucleophile. We'll talk about nucleophile strength a little bit later. What are we going to form here? Little leaving group left. Can I show the spectator ion with I minus? That's K plus I minus. Okay. Everything's there. If you try to do this with the F here as the leaving group, your reaction is going to be very difficult. It's impossible. I'd probably just say impossible. F is a very bad leaving group. Okay? Let's get rid of this. F minus. Does that make sense? Does it make sense that this doesn't want to form? It's the same nucleophile. So the difference must be that this doesn't want to be kicked off and formed. But apparently this does. Why is that a better leaving group? I want to explain.
It's larger. If it's larger,
and thus
there's more space between
and thus
the bonds, so it's
and thus more stable. We mentioned that week 1 of the course, right? Okay. Well, is this not stable at all? It's the most electronegative atom on the periodic table. Are you saying it doesn't like being minus?
no, but
Well, actually, that's what we mean. Because that prefers to be minus more than this. So you got to understand, but I thought it was the most electronegative. What does that mean? Well, you have to think about that. Okay, get you a cup of coffee with some anti-cancer compounds. It's the most stable, even though it's not the most electronegative because of the size. All right? You got some conflicting information here. It turns out that F minus is just bad leaving group. It doesn't like to be F minus. It's just small. Okay. That's an absolute comparison. We're just basically giving you an example of this is a better leaving group. Thus, the reaction is going to be easier. What really makes it easier? The transition state, right? You're going from product, starting material to product. You have maybe with iodide. Don't draw this. It's not going to be complete enough. Try to do with F, it's going to be like this. But why is the transition state higher? Because in the transition state, this bond has to break. But that bond breaking is just, well, one reason the CF bond is stronger. All right? But the other argument is where it's going to, it doesn't like where it's going to. And the system knows that, and so it's going to be hesitant to do it. Okay? It's like trying to get me to go through the haunted house. I'm not just going to do it. You're going to have to push hard to get me to go there. You're going to have to push real hard. And sometimes you may not be able to push that hard. And I'm not going to do it. And if I'm not going to do it, the reaction is going to become impossible. Okay, What about other atoms? What about oxygen? Can oxygen be a leaving group? If you take the same nucleophile, can this oxygen kick off this oxygen? SN2, bam, backside, kick it off? No, no reaction. That would give that bond, right? In this scenario, I'm replacing one oxygen with another. We form hydroxide, potassium sits with it. No. OH is a bad leaving group, okay? A poor leaving group. This reaction is not going to take place. Okay? How does hydroxide compare to maybe I minus? Not as stable. Is I minus more stable? It's more electronegative, larger? Yes. I mean, think about these. Which one wants to go back to neutral more? That. They would love to find something like an H plus to go back to neutral. That's why this acts as a base. I minus is really not basic. It doesn't want to go back to neutral. It's happy as it is. In the end, hydroxide is a poor leaving group. Okay? You got to be careful though. Hydroxide will not act as a leaving group in a slow rate determining step. Does the leaving group leave in this slow rate determining step in an SN2? Yes. So it's not a good leaving group for SN2. There are some reactions in which leaving groups leave in the fast step. If that's the case, hydroxide will leave. Okay? Because the fast step is much faster and easier. Right? Hydroxide will not act as a leaving group in SN2. No, SN1. How do we make oxygen a better leaving group? Can we? Yes, you can. If you include acid. Okay? And this is going to be H plus a catalyst. Now you got to be careful. It doesn't always have to be catalyst. You know the definition of a catalyst. Okay. H plus though. And H plus, the leaving group is actually going to be not hydroxide but water. And let's see why. Because the first step you're going to do here is before you do the substitution reaction is you're going to just do an acid-base reaction with the alcohol lone pair. Sorry, let's broaden that out. With the oxygen lone pair. It doesn't have to be an alcohol. Okay. Importantly, is I've mentioned you got to get past the idea of any example has limitations. I see students like focus on alcohol, and then when you see another oxygen, it's like, well, that's not alcohol. Apparently, you can't do it. No, you can. The broader thing we're doing here is we're propionating an oxygen. Okay. Propionate the oxygen. That's just an acid-base reaction, right? Okay. Good old acid-base mechanism. I'm just having H plus. It could be HCl. Well, what is H plus? What are examples of H plus? When you see H plus, it typically means strong acid. It doesn't have to. But what are examples of strong acid that could be used here? I'm just going to say strong acid because it can vary depending on what you want to do. We'll see examples. Type of strong acid. Get to here. We need to come back and talk about this. But from this point, what's the nucleophile? This here. And these electrons then come in here and bam, kick off the leaving group. But it's not hydroxide that's leaving. When this gets kicked off, what's being formed here? Water. Okay? water is being formed here. Much easier if water is neutral, it's more stable than hydroxide. All right. Before we get there, what does this arrow movement give? Does it give product directly? No, not yet. Bam, bam, there's our carbon. And then what's now bonded to the third carbon? Oxygen. But what's on the oxygen?
Hydrogen and a methyl.
An H and a methyl, and one lone pair left. And that is a positive oxygen now. We don't magically lose methyls, H's, or anything. We made bond between oxygen and carbon. There it is. Everything else is the same. Plus water. I can say plus water. Sometimes you might see it written like this. I just did it because I had more space to write like that. Okay. We lost water. There it is right there. That's what we formed. But now, how do we get to the final product? What do we have to do? Lose the H. What can take the H?
Water.
Actually, water could. Yes, we talked about that before. What if we had used something like sulfuric acid here? Okay. What if we had an HSO4 minus? What could take the H? It could be HSO4 minus, right? And if this act takes the H, and these electrons stay behind, and many of you are not showing the second arrow here, we got to show the electrons moving on to oxygen. What does that give? Final product, yeah? But what do we reform? H2SO4 reformed. And so in this scenario, the H plus was a what? Catalyst. It's reformed at the end. So in this example, the H plus actually is a catalyst. And how did it make the reaction easier? It made the leaving group better. How many steps does an SN2 reaction have? How many steps?
One.
Well, why am I showing 3? I got 3 steps. What are my steps? Protonation of the oxygen to make it a better leaving group. Then what did I do? Then I did SN2. Then what did I do next? I removed an H. Only the middle step is really the substitution. What we have here, we had a pre-step to activate the leaving group, and then we had to take care of the proton afterwards. Because in replacing this with something else, how many steps did it take to replace this with something else? 1 step. That is the SN2 part. So don't confuse that I did 3 steps and say, well, that's not SN2, it's not 1 step. There's activation steps. Okay. And if you were doing a reaction coordinate diagram and you say, well, it's SN2, and then I see some students who just want to put one step on the reaction coordinate diagram. No, it's 3. You have 3 steps on the reaction coordinate diagram. Okay? So don't confuse the fact that SN2 is said to have 1 step with us doing 3. It's not all SN2 up there. Yeah? Questions? You see how the acid is acting as a catalyst? How it helped make the leaving group better, and it was reformed, so it is a true catalyst? Question?
If you use an acid such as hydrochloric acid, would it be possible for the chloride ion to act as like the replacement group?
The nucleophile? Yes, it could. That's why I went over here. I was like, I'm just going to say strong acid because we got to talk about things like that. Yes. Because in my case, I use sulfuric acid because what do we know about this? Will this ever act as a nucleophile? No, not in this place. Not in alkene reactions, not in this type of stuff. And again, guys, I try to teach holistically. I don't do alkenes and then forget about it. Everything it's a lot of the same information used throughout the course. You pick it up on that? Okay? So that's how I want to present it. So we learn how to use it whenever we want. Great question. CO minus, we've used that as a nucleophile before. Very valid here. I didn't mention it, but back over here we used methanol as the nucleophile. Up here we used methoxide, the anion. Why did we use methanol here? Why not do this reaction like over here, top? Why would that not work? The H plus is there to make the OH group a better leaving group. We can protonate it, make it a positive oxygen. In the end, a neutral oxygen won't leave, but a positive oxygen will. Pick up on what we did here? It's more willing to leave because when a positive oxygen leaves, what does it become? A neutral oxygen. Okay, so it's willing to leave. All right? That's more of the broader thing to see there. We made it positive. Then it's, okay, now I'll leave because I want to get my electrons back. And one way to get my electrons back is to steal them from the carbon. And it's ionize away, leave. Why won't the top reaction work? I've got the acid to make this a better leaving group. Don't I have a nucleophile? Can the OMe, the methoxide oxygen, come in and kick off the water? Anybody? The reason this won't work is the same reason you can't fill your bathtub with hot and cold water and then think there's hot water there and cold water there. Not. This is the base. O minus is just like hydroxide. That's a base, right? Methoxide's a base. Methoxide will react with the acid. You can't have your cake and eat it too. You can't have a base in the reaction and then start adding an acid catalyst. Those two will just react. Those acid-base reactions are very quick. Substitution reactions take a little time. Period. Okay? Not compatible. So instead, we need to use the neutral oxygen. With the H there. Okay? Don't write this. Just show you got it there. Right? They're both oxygens with lone pairs. This is the neutral form. This is the minus form. This is basic. It can't exist with acid. But this can exist with acid. Okay? Now please be careful. Methanol is not ionic. Some of you try to show it ionic. It's not. Just like water is not ionic. Okay? All right. So that's the problem. You can't have your cake and eat it too. Let's expand upon this. Other typical reactions here. Alcohols, and I'll erase this. This is reacting with HI to give an alkyl iodide plus water. Now this reaction will work. It's a very common reaction. Can you show a mechanism for this? First off, is OH a good leaving group? Because it apparently left the carbon here. Is it a good leaving group?
No.
No, we said that. How do you make it a better leaving group? Protonate it with a strong acid. Do we have a strong acid available? HI is a strong acid. You can just show this ionized, H plus and I minus. And we can protonate. We've already done this previously. Get to that point, right? Now the I minus, what do you want to do next? At this point, now we consider substitution. Now we have a good leaving group. Now we can do substitution. Is it going to be SN1 or SN2? SN2. It's primary. We've already answered such questions. Now what? This comes in here and does what? Kicks off the leaving group. What does this give? There you go. right? We're done. So the HI is one molecule, it's one reagent, but it supplied both the acid and the nucleophile. It's a very common reaction to react alcohols with hydrohalic acids and convert them to the corresponding alkyl halide by this type of mechanism. And you mentioned chloride attacking. Well, this is iodide attacking. You can do the same type of reaction with HCl. It's happening with HI, do it with HBr. Do you think it will work with HF? It's a strong acid. But F minus is a poor nucleophile. But we haven't actually said that yet. We said it's a poor leaving group. It's also a poor nucleophile. Okay. Question. Is the H plus the catalyst in that reaction? No. We didn't reform it, did we? So, not actually a catalyst, because the definition of a catalyst is you reform it. So it's not a catalyst, what did it do? Didn't it make the leaving group better? Sounds like a catalyst. Made it better. It's like a pseudo-catalyst. It's like, but you can't officially call it a catalyst because the definition of a catalyst is that it's reformed. Right? I just made that term up. I've never heard it before. Maybe an activator, promoter. There's other terms. Once you say catalyst, that has a strict definition. Okay? You like pseudo-catalyst? Run with it. And when you get famous, just remember me. What do you mean pseudo-catalyst? Well, then you can explain. Then you get someone to listen and explain. Okay? Okay, you want to show a product? Let me ask you, does the oxygen have to have an H on it up there? We never talked about the H up there on the starboard material. We talked about oxygen being protonated. Expand that out. This has an oxygen. There's no H here, it's not an alcohol. Can you protonate this? Okay. Do the same chemistry. Show a product here. At this point, let me talk to you about, okay, you got to assess your reagents. You got to assess what type of reactivity can you do. And that will be more important going forward. Alkene reactions, a lot of them you can kind of just memorize. Okay, alkene, BH3, that's going to give an antimicrobial hydration. The type of reactions we're doing now, you can't memorize as much. You have to assess them. Okay? What do we have here? I have a strong acid. Very often you're protonating something, the H plus type of thing. What can you protonate here? Oxygen. Once I protonate it, because I guarantee you guys, if you got a strong acid, usually you're going to protonate something in your mechanism. And usually it's the first thing to do. From there, what can you do? Well, at this point, we only know one thing, so just do it. So, anybody have products here? Yeah. Anybody predict products here with your mechanistic knowledge? Where's it? Once you draw it, once you draw it, you may see the test are written, not verbal. Practice writing things down and then assessing, did I get it right? Somebody got it?
Oh, okay.
Nope. Got it? Nope. 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 Anybody got it? Anybody got it? Sorry. Nope. Nope. Anybody got it? Anybody? Nope. Nope. Okay, at this point, I'm going to refer you back to page 1 of the handout. At the very top, in bold letters, what is the, not the warm-up page, the back of the first page. It's underlined, it's at the very top, it's underlined, it's in bold. Somebody please read it. Somebody, real loud, go ahead. Tetrahedral carbon. Yes, okay, now do you want to redo your, yes. Okay guys, SN1 and SN2 are substitution mechanisms that take place in tetrahedral carbons. All right? You do not do these mechanisms on trigonal planar carbons. Tetrahedral is going to be sp3 carbon. Okay? Can I get to this point? Can I just protonate this without wasting 30 seconds of valuable class time? Anybody know how to protonate nitrogen? Okay, you can't skip that step on a quiz or test. But I'm going to skip it in classroom now and to save us some time. At this point, what's the next step? Br minus can come in here and kick the oxygen off of a carbon. Why did you all attack this carbon and kick off the oxygen that way? Is it this because the OH was kicked off to the right on my example? I think probably so. But look, which one? Okay, you have two choices. You can attack this carbon and kick the oxygen off of it, or attack this one and that one. Which one of these is tetrahedral, sp3?
Right.
Correct. You attack here and kick off the leaving group. What does that give? Gives that, which was the leaving group. Plus what? Plus ethyl bromide. That's 2 carbons of bromine, right? I mean, I do not have to draw it like that, do I? However you want to draw it. Ethyl bromide, right? You're looking at it strange. That's 2 carbons with an oxygen bonded to it. Well, that's 2 carbons with not an oxygen, but a bromine bonded to it. The bromine replaced the oxygen. Right? Very good? Did anybody get these? Now, in this case, the leaving group is not water. It's a pretty big molecule. Again, think generally. We protonated an oxygen, and then a nucleophile kicked it off of a carbon. But we had to choose which carbon. And the choice here is easy of only tetrahedral. What if you had 2 tetrahedral carbons to attack? Then either could be attacked. Are there reasons you might choose one over the other? Sterics. Sterics is an important factor. If one was very sterically congested and the other was not, which one would you attack? The one that's less sterically hindered. Okay? Are we good? That was A. What was A? Well, you should look and see. B. Another way to convert OH to a good leaving group is to convert it to a tosylate. Pseudohalogens. I knew that term was coming. Pseudo. What is a pseudohalogen? Not exactly a halogen, but it's very kind of like it. Similar characteristics. Yes. We know halogens are a leaving group. These things are kind of, they become more halogen-like. A tosylate is this thing. The oxygen bonded to the rest of this. The whole thing is called that. I abbreviate this as O-tos because that is tosyl. With the oxygen added there, it would be O-tos or fully tosylate. Now, I'm the only one that does O-tos. Strictly, it's O-ts. Though I like to say tos, so I put the O in. Okay. Okay. So the textbook is probably going to say O-ts. All right. Now, this whole thing is a good leaving group. Just like an iodine is a good leaving group. And you do not have to protonate it. It needs no acid. It's good to go. And so nucleophiles will come in here and kick that oxygen off. When it gets kicked off, what is formed? What does the leaving group look like? You can show that. Okay? Does it form that? Right? That takes on a third lone pair. Another third lone pair. You're looking at this funny? What is that? That's just a Greek for phi, P5O or something like that. Okay? This is a generic for an aromatic ring. I just didn't want to waste ink and time in drawing the big aromatic ring. Alright? You know how we use R as a designation for like a big alkyl group? Okay. The symbol there, phi or phi or whatever it's called, is a symbol for an aromatic ring. Now you need to know what a tosylate is. Why is it called tosyl? Well, what is just benzene with a methyl? You used it in the Diels-Alder lab. Toluene. Toluene. And SO2 like that's a sulfonyl. And with the O minus, it's kind of like 8. Phosphate, that type of ending. Toluene sulfonyl. At some point that got shortened to tosyl. It's a shortened form of toluene sulfonyl. Everybody get it? Okay, that's where tosyl comes from. It's got the toluene group. This is toluene here, designation for an aromatic, just like R group. Okay. Why is this a good leaving group? If this was OH, it would not be. Compare this. Why would tosylate serve as a leaving group but hydroxide not? That apparently means it's more stable, more willing to form. Why is it more stable? Resonance. Lots of resonance stabilization here. And the charge is delocalized onto what other type of atoms? Other oxygen. Very delocalized. This kind of looks like what is this? This is the conjugate base of sulfuric acid, which is very stable. That's why sulfuric acid is a very strong acid. Very stabilized. The only difference is this OH is replaced with a toluene group. Okay? It's a very stable anion. It's a great leaving group. Similar to bromine and iodine. That's why we call it a pseudo-halogen. Okay? This is the most common one at the intro stage. There are others. Your book may or may not contain these. If there's a methyl out here, it's called a mesylate. Does that make sense? A methyl sulfonyl. If it's a CF3, that's a trifluoromethyl sulfonyl. Trifluoromethyl sulfonylate, it's shortened to triflate. And that's actually the best one because these fluorides out here, you got all these fluorides out here, it also stabilizes the anion by induction. Okay? You're probably not going to see triflate in your textbook. It's more common at the upper level and research level. It's a little expensive to use. The other two are cheaper. Tosylate is the main one at the intro level. You can also use these guys. These are esters of sulfuric acid. That is, instead of being methyls here, if those are H's, that would be sulfuric acid, right? We can replace the H's with methyls. And now, a nucleophile can come in here and kick off the remainder, because this oxygen, when it leaves, It'll look like this a lot. It'll look like this, except the other one will be a methyl. And you can also do ethyl. The reason to show those is those are very cheap. You can buy like gallons of those for $10. And so since they're cheap, they're very common. But it's very analogous to tosylate. And they're esters of sulfuric acid. Okay? As you attack the tetrahedral carbon and kick off the oxygen, because it's stabilized by resonance. Now, those are also pretty toxic because they're so reactive. And they're like double reactive because you can actually attack that carbon and kick this one off. You can attack on both ends. Where with a tosylate, there's nothing to attack over here. You only attack the tetrahedral. There's only one tetrahedral carbon in the leaving group. There's actually two in those things. Okay, let's get to tosylate and do some chemistry. Stereochemistry. How about if we react this with tosyl chloride pyridine? This is how you make tosylates. Tosyl chloride is just Cl. Remember, that's tosyl and tosyl chloride. And the first step here is the oxygen reacts and kicks off the chlorine. You can look through this chemistry and draw out your O-tosylate. Okay? It is a substitution reaction, but it's not SN1 or 2. Okay? Under my hand is chlorine. Whenever this reacts, it kicks off the chlorine. Now under my hand is oxygen. Okay? And if under my hand is oxygen, we now have this. You need to look through it. Okay? I'm not going to do this mechanism here because it's a new mechanism we don't need to get into now. We will look at it in organic 2. Okay. There are other types of substitution mechanisms. The only ones we're covering here are SN1 and SN2, which occur on a tetrahedral carbon or tetrahedral atom. That's not a tetrahedral atom. Okay. In the end, importantly, whenever you make this, there's no change in stereochemistry here because the oxygen is interacting with the sulfur. The oxygen is now bonded to the sulfur. No chemistry took place here. Now when we do the SN2, what do we get? Take that off, and how's the nucleophile going to be bonded? The leaving group is forward, so the nucleophile came in backside, and back. So SN2 comes with inversion, right? We already knew that. Okay? Just like you knew Big Mac comes with fries. Okay? Big Mac comes with fries, SN2 comes with inversion. Okay? One big happy meal. Okay? But in this case, you can't make substitutions in your order. Can nitrogen be a leaving group? So halogens, oxygen. How do we make oxygen a better leaving group? A, protonated. Another way to make OH a better leaving group, convert it to a tosylate. What about nitrogen? Can it be a leaving group? Many atoms can be, and we're looking at different atom types. Much less common. Much less common. But here's an example. Try that mechanism on your own. See if we can look at it. What about sulfur? Can sulfur be a leaving group? Much less common. The most common leaving groups, guys, are your halogens. And oxygen is pretty common. But with oxygen, you have to do what? Protonate it or convert it to something else that's better, like the phosphate. Those are your most common leaving groups for SN1 and SN2. But there other atoms can. Nitrogen can. Sulfur can. With sulfur, it's good to look at because your body uses sulfur as leaving groups. And so biochemical related. Here's an example. Everybody know this compound? Name that molecule, you could do it. Maybe not. Norepinephrine. Your body produces norepinephrine and then it converts it to epinephrine. Okay? What's another name for epinephrine? Very good. Adrenaline. Yeah? Talk about this in biology.
Anatomy.
No.
Anatomy.
What?
Anatomy.
Good. Okay. Yeah. Over in Europe, they use the term adrenaline more. We call it epinephrine in the United States. I don't know how that happens. Yes. Adrenaline and noradrenaline. Yeah. What does nor mean? What's the difference in these molecules? A methyl group has been added. Nor is where something has been removed. This is a term that's used in terminology. You go this way, you go from here to here, what do we remove? A methyl. Hey, something's been removed. Let's just call it a norepinephrine. Okay? All right? Or noradrenaline. Using the nor indicates something has been removed from the non-nor compound. Okay? How does your body put a methyl on norepinephrine? It uses this guy called SAM. S-adenosine methionine or something. It's got an amino acid. It's got a nucleic acid type thing. But right here, you got a positive sulfur with a methyl. And this can act as a nucleophile and attack the tetrahedral carbon and kick off the positive sulfur, analogous to kicking off a positive oxygen. Yeah? You make sulfur a better leaving group by making it positive, just like. Okay? But your body does things like this and uses sulfur as leaving group. How is SAM formed? Well, that's a different question. Okay? But actually, SAM is a supplement that you can actually take. Your body produces it, but if you want to have more of SAM in your body, maybe you want to produce more adrenaline or something, and you want to supplement, you can go to the drugstore and you can buy a bottle of SAM. Okay? And then you can say, because I want to do this chemistry more for some biological reason. So, here's an example of an SN2. Hold on, this has to lose an H. So you have to look at that mechanism, because when this makes another bond, the nitrogen becomes positive. To go back to neutral, it has to lose an H, so I'm skipping that step. There's an additional step there. But SAM is serving as a methylating reagent. Does everybody agree that more terminology, methylating reagent? Can we use that term? Is that what it's doing to the starting materials, like methylating? Can we broaden this out? What if it's an alpha or propyl? Can we call it an alkylating reagent or agent? Isn't a methyl a specific type of alkyl? So if you ever hear SAM or such molecules called alkylating reagents? Alkylating agents? Is that what they're doing? Yeah. SAM is an alkylating reagent. Okay, let's finish up here, guys. Nitrogen sulfur leaving groups. An application here. Ever heard of sulfur mustards? Okay. Very toxic. Very toxic. Used as war gases, unfortunately. These things here, this molecule, this sulfur here comes in here and kicks off the leaving group. Now, here I did it on the other end. I could have did it this way as well. And it makes this three-membered ring. But then your biomolecules can come in here and attack the tetrahedral carbon and kick the positive sulfur back off. Okay? SN2, right? And now your biomolecule has been alkylated, and this leads to bad news. It's also going to produce HCl, which is bad news. You start producing HCl in your lungs. Okay? There can be questions about this, but we're pretty much out of time. We'll pick up here. Take a look at that. Very important application. The compound on the right is actually a drug used to treat cancer. That's where you actually want to have some toxicity. You want to kill the cancer cells. And so this can be used to kill cancer cells. We'll mention this next time. Quiz on Friday. We will not put any substitution on it. I'll refrain from doing that. Okay. Dyne reactions, resonance, mass spec. That's the three main topics we got. We haven't done that. I can't hear you. Not the part I didn't. No, not that part.